All right, elimination reactions. This time our products are going to be double bonds. All right, here are the two type of reactions. You have an E1 elimination and an E2. Mechanisms are very similar. A lot of these reactions are very similar to SN1 and SN2s as far as nucleophilic strength, as far as the type of carbocations. You form carbocations. You can get rearrangements in the E1s because you form carbocations. As for and the rate of the reactions, a lot of things are very similar. Okay, so for an E1, notice you've got a tertiary carbon. All right, see it's tertiary, it leaves, you form a carbocation. Excuse me. You've got a weak base. It's weak because you don't have a negative charge. Notice it's plucking off a hydrogen next door to the carbocation this time to form a pi bond. All right, this is a unimolecular reaction because it's E1. Here, this happens. It's stepwise. This is a concerted mechanism because it happens all at once. Your nucleophile comes in, forms a double bond, kicks down. This is usually big and bulky. They're not showing a bulky one, but usually you'll want a big and bulky one because remember you're trying to get away from substitution. Also notice this is also tertiary. You notice that? That's the difference. Okay. In this case, all right, we've learned the SN1 and E1. You want tertiary greater than secondary greater than primary. Well, guess what? E2 is exactly the same thing. Why is that? Because you want this to be hindered. You don't. If this was a primary, you would have a SN2 reaction as a competitive reaction. So you want bulkiness. You want this to be bulky. If you do have something that's not bulky, then you start changing your base and you make that very large. All right, so elimination reactions produce double bonds, also called dehydrohalogenation. Let's first talk about the E1 reaction. Unimolecular. Okay, two groups lost, a hydrogen and a halide. Nucleophile acts as a base because it's plucking off hydrogens. E1 and SN1 reactions have the same conditions, so a mixture of products will be obtained. So, you know, when you do an SN1 reaction, you actually get a little bit of the E1 product. You can't just say, I just want SN1. I don't want any eliminated product. Obviously, chemicals are going to do what they want to do. You can't change how like nature works. So these are actually competing reactions. They happen at the same time. There are ways to kind of favor one or the other, but pretty much they happen all the time. Okay. So let me go back. So the rates, they didn't really show you. I thought they would show you the rate equation. They might in a different slide, but the rate again is dependent on your electrophile. Remember, it depends on how quickly the leaving group leaves. So here's basically the mechanism. The halogen leaves, your halogen leaves to form a carbocation. Your base then, all right, remember for E1 you want a weak base. Also, I would have it bulky. I would have as big as possible. Okay, common one is tert butanol. Okay, so which is basically a carbon here with 3 CH3s around it. So that's a gigantic molecule to form your double bond. Okay, here's kind of a closer look. They just kind of show you how the overlapping orbitals. Some people are interested in this. I really don't have a desire to really look at it. Energy profile, very similar to SN1. It's a two-step process. Your rate determining step is your first step. You form an intermediate, and then you have the faster step as your second step. Okay, let's talk about substitution patterns because this becomes important. All right, this is what's called tetra-substituted because it's a double bond with 4 carbon groups attached to the carbons in the double bond. This is tri-substituted. You've got 3 carbons. Di-substituted, 1, 2, or you got mono-substituted. All right, this is more substitution. This has a higher substitution. This has a lower substitution. Why is this important? Because when you form a double bond, if the double bond can form 2 different products, it's going to form the more substituted double bond product. This is called Zaitsev's rule. Okay, Zaitsev's rule. And I'm sure they're going to show you an example of Zaitsev's rule. Okay, if more than one elimination product is possible, the most substituted alkene is the major product. So notice I have a positive charge right here. I can eliminate this hydrogen, hydrogen 1, or hydrogen 2. Okay, well hydrogen 2 leads to this compound right here. Notice this double bond is di-substituted. If it eliminates hydrogen 1 and forms a double bond here, it's this product. Notice I am tri-substituted. So this is going to be my major product. If I have two possible answers, the one where the more substituted double bond is our major product, because this is Zaitsev's rule. Zaitsev. Okay, it's fun to say. Zaitsev just kind of rolls off the tongue. Okay, so that is Zaitsev's rule. Remember, anytime you form a double bond, you want to form the more substituted. This, they don't show it in here, but this is actually called the Hofmann product. We're going to talk about this next semester, for those of you that take the class next semester. The Hofmann product is the least substituted, and you can form that. There are reactions in which you can form that. Well, that's next semester. All right, here they kind of show you the competition between E1 and SN1. Okay, basically it's the same thing, right? What do you need for an SN1? Tertiary carbocation and a weak nucleophile. Well, what do we have here? Tertiary and a weak nucleophile. Okay, well, how do you think you would get away? So notice you get both products, the eliminated product and the SN1 product. Okay, in order to get away from this, the best thing to do is to make this into a large group, a big bulky base. So like I said on the last slide, tert-butanol. Use something like this. Okay, because I don't want to attach this onto my ring, I don't care what this is. If the bigger this is, the better. Because imagine trying to get this oxygen now into this carbon. Not only is this tertiary, but this is tertiary. These two will never bond. Okay, so this is kind of what you want. Another way to enforce more eliminated product is to heat the reaction. So two things to get more E1. Heat it, and number two, a bulky base. Okay, the bulky base should be the number one, and the heat should be number two. You really want to try to get a bulky base. So it just shows you here that substitution results from nucleophile attack. Ethanol serves as the base in elimination as well as a nucleophile. Okay, so the carbocation can react with its own leaving group to return to the reactant, which we don't really have to worry about that. Reactant with the nucleophile can form an SN1 product, lose the proton to form E1, rearrange to give a more stable carbocation. So you can get rearrangements. So, like I said, for E1s, if you want to favor E1, now notice E1 and SN1. What do you need for both of them? Tertiary, weak nucleophile. So you're going to have competing reactions, just like the last slide. But to favor the E1, you want to heat it and add a bulky base. Okay? To favor SN2, don't heat it and don't add a bulky base. Just the exact opposite. Okay? So, E2 reaction. Again, elimination, it's bimolecular. This requires a strong base, just like it does in SN2. And again, you're going to want this to be bulky. The larger you get, the bulkier, and heat. Same thing. Okay? It's a concerted reaction. The proton is abstracted. Same thing, you get Zaitsev's rule. Zaitsev's rule follows, but notice in this case, it happens all at once. Rather than this leaving first, this is going to pluck off, and this is going to leave at the same time. I think they forgot the arrow here. There should be an arrow here. So as the base is plucking off the hydrogen, the electrons go here, and this falls off. What we're going to see is that this hydrogen has to be anti-periplanar of the leaving group. You have to have this opposite effect. If your hydrogen was here and you try to pluck off that hydrogen, that will not react. It's got to be what's called anti-periplanar. You remember when we looked at Newman projections? Okay, we called this the anti-product, where you had, let's put a bromine there. Okay, you wanted this group to be anti of this group. That's what anti-periplanar is. So if you look at this as a Newman projection, this is basically how it looks, except the hydrogen is going to be on top. Okay, but it's basically, that is what you need, and I'm sure it talks about this on the slide. In this case, tertiary goes faster than secondary, goes faster than primary, just like the E1, just like the SN1. The reason is because you want the bulkiness. Bulkiness is the key for elimination. Always think of bulkiness. Okay, mixtures may form, but Zaitsev product predominates. Stereochemistry: the halide and the proton to be extracted must be it calls it anti-coplanar, anti-periplanar. It's the same thing. In order for the elimination to occur, because the orbitals line up. You can read all this on these slides that I posted, but there's nothing here that I haven't already talked about. So this is kind of showing you, look, they even show you Newman projection. This hydrogen is anti-coplanar. I'll use the words they use, but periplanar is the same thing. Opposite of the halogen. See, the hydrogen is opposite of the halogen. Okay? And the reason is because you have this overlap. You have the overlap of these. It's kind of like a hyperconjugation effect in a way. All right, the hydrogen here is kind of sharing its electrons into the antibonding orbitals. We didn't really talk about that, but in this case, you have a repulsion between the base and the iodine. This is perfect. As your base is coming in, it's going to repel against your. And remember, your halogen, they don't really show it justice. Is like that, you know, it's gigantic. Okay. So that's why you want it anti-coplanar. Okay, so the difference between the mechanisms, tertiary is greater than secondary. Base strength is unimportant in the primary. It's usually weak. So this is for E1s. E1. Secondary is faster than secondary. For E2s, you're going to find out same exact thing. I'm sorry, tertiary is faster than secondary. Base strength is unimportant. Usually want weak. You also want bulky. Again, your book does not discuss this, but that's what you want. Don't worry about the solvent choices. We're not going to worry about solvents. The rate is just dependent on the alkyl halide, Zaitsev's product. The geometry is not important. You do not care if this is anti-coplanar because you form a carbocation. Rearrangements can occur. For the E2, notice you still want tertiary because you want bulky. Base strength, you want a strong base, but a bulky strong base. In this case, you'll want something like that, butoxide. Okay, solvent, don't worry about that. Rate, remember, is dependent on both concentrations, Zaitsev's products. Coplanar, you want these to be anti of each other. And there are no rearrangements. Okay, substitution versus elimination. This slide is very confusing. There's a lot of words. In class, when we go to class, I'm going to break this down to you in a nice little chart that will make a lot more sense. Okay, again, remind me to do it in class. Okay. But pretty much strength of the nucleophile, it determines the order. So strong nucleophiles or strong bases are SN2s or E2s. Primary halides are SN2s. Tertiary halides are either SN1s, E1s, or E2s. It depends on the strength of your nucleophile and the size of your nucleophile. Strong nucleophiles favor E2. Weak nucleophiles prefer E1 and SN1s. Okay, but if it's big and bulky, it's going to prefer E1. Okay, high temperatures favor elimination, and hey, they do have bulky bases. Look at that. Bulky bases favor elimination. Okay, so the bigger, the better. Secondary alkyl halides is kind of the weird one because primaries and tertiaries are obvious. Primary, SN, so if you have a primary alkyl halide, that goes SN2s. Tertiary goes pretty much SN1s or E2s. I guess E1s too. But a secondary, what does that do? What does that favor? All right, it favors everything. It just depends on the nucleophilic strength. So the secondary alkyl halides are more challenging. Strong nucleophiles are the 2s. Weak nucleophiles are the 1s. That's pretty much straight, and it's cut and dry. Okay, strong nucleophiles with limited basicity favor SN2s. Bromides and iodides are good examples. Okay, these are just kind of showing you SN2 versus SN1 type of reactions. Okay. All right, so here's a problem. Predict the mechanism. What mechanism is this going to go through? What do you think? Okay, so you analyze it. You notice you have a tertiary here, and you have a weak here. So tertiary and weak, and you have heat. What do you think is going to predominate? Okay, well, tertiary and weak, really, mechanisms are SN1s and E1s. The fact that there's heat here is making me think that it's going to favor more of the E1 compound. And based on Zaitsev's rule, you're going to get the more substituted alkene, which would be that one. The SN1 product, just to kind of show you, just for completeness, this is what the SN1 product would look like. Okay, let's put the CH3 here. However, I would guess, based on what they have here, that this is the major product. Okay, so the solution, all right, they actually show you both. They show you the E1, here's the major product, which is what I said, and then you also get the SN1, which is the substitution product. But I'm assuming that the blue is the one that they're showing is what's happening here. Okay, so notice, and it's all because of the heat. What I would do, now if it was me, if I wanted to favor this compound, I would not use this base, I would use the big bulky base. So I'm hoping you're starting to see how you can favor one or the other. These reactions do kind of compete against each other. There's really nothing that you can do about it. Solve problem 2. Okay, predict the mechanism and products. This time I have a secondary carbon, and I have a strong nucleophile. Remember, anytime you see a sodium, just ignore it. There's a minus charge. And it's small, and I do not have heat. Secondary, strong nucleophile, no heat, it's small, SN2. There is no doubt about that. That is SN2. This is going to come in right there and kick out your bromine. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 with the OCH3 right there. SN2 reaction. It could go E2, I guess. You could form E2. Why don't you draw what the E2 product should be? Try to think about what the E2 should be. I'll give you 10 seconds. I'll give you 5. All right, it's going to look like this. 1, 2, 3, 4, 5, 6. Double bond right there. Notice you can either form a double bond here, okay, or a double bond there. This is more substituted right there. All right, so they show you the E2 products and the SN2 products. They don't really tell you which one's the major, which one you get, but you're really going to get the SN2, I think, because of the size and you don't have heat. Okay, so that is the end of this chapter. There is a lot of information in this chapter, and it's not as cut and dry as other chapters. But like I said, come with questions, and we will go over all this stuff. See you in class.